introduce Dr. Alan Song, who's going to give feedback on his SIGNA ultra-high performance 3T system, which shares many of the same components as we have on the SIGNA 7T. So Dr. Song.
Good morning. It's a great pleasure to be here. Thank you, OHBM, for hosting and GE Healthcare for inviting me to join this virtual platform. My talk today is centered on high-resolution diffusion MRI on the SIGNA UHP platform. And the reason we do this is basically motivated by our interest in neurodegeneration, which is a primary focus of the Brain Initiative. The prerequisites for high-resolution diffusion MRI are multiple. I'm listing three here, the three primary ones. The first is strong gradient strength, and that is going to give us high diffusion weighting efficiency, which leads to short TE for high SNR and short readout window for sharp point spread function and high throughput. The second is high channel count RF array. We want to have that type of RF coils for high SNR, high acceleration factor, and deep brain coverage with large air coil element. Because of interest in neurodegeneration, deep brain regions are very important. For example, hippocampus, basal ganglia, thalamus, and also it's important for us to use air coil elements to have deep penetration. And the third is fast imaging sequence, which allows to break the spatial resolution limit so that we can get to ultra high spatial resolution to delineate very fine microstructural changes. However, when we increase the spatial resolution, we would then increase the imaging time, which can be very impractical at times. So we also want to develop multi-band or simultaneous multi-slice SMS imaging to increase imaging speed. So first up, strong gradient coil. With GE's support, we were able to install the Ultra G gradient coil in our MR750 bay. So this is basically one of the centerpieces of the UHP scanner. In essence, UHP scanner is really a combination of this Ultra G 60 centimeter gradient coil with the Premier 3T platform. With peak strength at 113 millitesla per meter and slew rate of 260, we can achieve the highest diffusion weighting efficiency for our high resolution work. So shown here are some of the pictures of our work in the November 2018, actually 2019, sorry. 2018. Sorry, the pandemic is really giving me a hard time figuring out what time we are. So this system has been working for about a year and a half flawlessly. One important aspect of this Ultra G gradient coil is the mechanical stability due to the torque balance design, as Bodave alluded to earlier. So shown on the left is our old MR750 3T with the older gradient coil. When you turn on diffusion weighting with an effect of 1000, you can actually see the water begins to ripple. And on the right is the Ultra G gradient coil in our UHP 3T. So the same diffusion weighting gradient. You can actually hear the sound in the background. The water surface is very calm, which is important to avoid any motion blur so as to achieve true spatial resolution. Okay. Now, as I was saying, we also need high channel count hair coil to penetrate into the deep brain region and also to enhance SNR. So shown here is a comparison between the 30 channel hair coil on MR750 by Nova and the 48 channel air coil hair coil on the UHP. The deep brain coverage is fairly obvious here, as well as pretty good improvement in SNR overall. And given that it's a 48 channel hair coil, it also gives a little bit of flexibility to achieve higher acceleration factor, whether it's through plane or in plane. So first up, we did some comparisons for sanity check on the diffusion data to compare with the lifespan HCP, which is gold standard diffusion data at 1.5 millimeter. We did the same acquisition, obviously with a little shorter TE, as well as about 30% shorter readout window. You can actually notice there's a little bit of improvement in the sharpness of the image, and that's likely due to the improved point spread function, PSF. for the shorter readout window, as well as reduced motion blur because of the stability. Since we have the Muse sequence to increase the spatial resolution, we were able to just do a quick check on the 1 millimeter as baseline. So in addition to the traditional white matter fibers, we can actually see the gray matter is showing up as well, in addition to the details in the deep brain regions. I want to give you a little bit of a idea of the raw image quality. So you can actually see with single shot diffusion, there's obviously significant geometric distortions in the base of the brain. While with Muse high resolution, not only we can achieve higher spatial resolution, but we can also reduce the spatial distortions in the traditionally inhomogeneous brain regions at the ventral brain region. I'm going to play a video going through slides from bottom to top, just to confirm that the fidelity, spatial fidelity is ensured throughout. And again, as I was saying earlier, the Muse diffusion protocol would allow us to study not just the white matter, but also gray matter in detail. And here is a comparison between the 1.5 millimeter HCP data and the 1 millimeter Muse data, providing much improved details of the gray matter column-like structures. I'm going to cycle through a video here as well, going from top to bottom, illustrating the greater detail in the gray matter column-like structures. So the color here is fairly standard with diffusion color scheme. Red is left and right, green is top down, and blue is through the plane. Not only we can achieve greater delineation in the gray matter fibers, we can also provide better characterization of the U fibers, which are of high curvature typically. It's hard for low resolution images to capture that, but we can do that pretty well. And even crossing fibers, when the superior longitudinal fasciculus and corpus callosum are crossing with high spatial resolution, the fibers are better delineated as well. As I was saying earlier, when you achieve higher spatial resolution, the price you pay typically is the lengthening of the imaging time. So in order to avoid the penalty of the throughput, we have also implemented multi-band. However, with typical multi-band implementation, we would see noise amplifications because we're stacking multiple bands on top of each other. Even with Kaipi or shifted field of view, there's still significant overlap between brain slices. So here we actually did a little bit of a change up. We use a rectangular field of view to create more empty space to slide the brain images into those blank spaces. The penalty obviously is slightly longer readout window, but it's not that bad. So we're talking about less than 20% increase in acquisition per acceleration. However, because our TR is fairly long for diffusion, there's really no penalty in the throughput. And here is multi-band acceleration factor 2, virtually with no noise amplification or G factor penalty, no penalty on the TE. So you can actually see the image quality is actually as good as single band acquisition. So with this, we can achieve 0.8 millimeter spatial resolution for the whole volume within 36 seconds. So that's pretty impressive. And with 3-band, we can actually reduce it further to 24 seconds. As I was saying earlier, we want to apply these techniques to understand or better understand the microstructure changes related to neuronal deficit in neurodegeneration. Shown here is a shot of gray matter fibers. If we take a small window and zoom into it, let's imagine we are seeing 3 cortical columns here. While we're working, normally our brain is firing, the neurons are working great. And if you take a little zoom in picture again, you can see all these neurons, which forms a fairly dense dendritic tree in the mid-cortical layers. And it's reflected by the fractional anisotropy, FA, profile from the surface of brain to the white matter, gray matter boundary here. Now, if at the early stage of the Alzheimer's, for example, when you have dendritic loss or cell loss, before the symptoms occur, you would then should be able to see some form of reduction of the fractional anisotropy due to the loss of dendritic density. So this is our hypothesis that we can actually pick up these early changes before symptoms occur, and hopefully we can achieve even earlier detection by using microstructural MRI. So we did some preliminary investigation before the pandemic. The work's continuing. So here is a group of 80 patients and control patients, age matched. So you can actually see the loss of FA or anisotropy in the mid-cortical layers going from the surface of the gray matter to the gray matter white matter boundary, as we were hoping. So this is encouraging, and you can actually see the column-like structures are well delineated at this 0.8 resolution. The reason we chose 0.8 is because usually the cortical columns are around 0.6 to 0.8 millimeter across in diameter. So it's a good spatial resolution to stay at. My second interest in neurodegeneration is Parkinson's disease. This work is actually inspired by our collaborator here at Duke, Miguel Nicolelis' lab. They found that by using spinal cord stimulation, we can actually alleviate or even remove the symptoms of Parkinson's disease. So in this rat model, they placed electrodes on the dorsal column of this mouse. And then by stimulating the animal in the dorsal column, they were able to restore the locomotion, which is one of the cardinal symptoms, for example, gait freeze. This work can be extended into humans in vivo. So shown here are 4 subjects with electrodes placed in the dorsal column in the joint section between thoracic spine and C-spine. Because we don't really know where exactly to place these electrodes, we did sort of a copy bombing strategy. 15 electrodes are implanted in these 4 patients, and then the one with positive and minus signs indicate the actual stimulation that we placed into these electrodes. So here, 7 electrodes are activated to achieve stimulation, but obviously you can use more electrodes just to achieve more white coverage. The hypothesis is that these currents would then travel upwards through the dorsal column to the deep brain regions, much like the DBS approach, except you don't have to open the skull. So here are just some examples of 4 patients. These 4 patients, you can actually see on the left, all patients had significant difficulties either initiating a move with gait freeze or initiated a turn. However, with spinal cord stimulation, SCS on, all these patients can actually work fairly well, and a great improvement is seen. So I was just saying, the mechanism or potential mechanism that we believe is that we can deliver stimulation through the dorsal column from the spinal cord to the deep brain region. And for example, STN, that's the same as DBS. The point of diffusion MRI would come to play is that as a normal implantation is concerned, we don't really know exactly where to put the electrodes in the spinal cord. However, if we know exactly where we want to stimulate in the brain, we could use that as a C point, for example, STN, and try to see where the fiber would lead us to the dorsal column. So we did an initial attempt to do that. Unfortunately, the fibers all terminated in the neck area, didn't go farther enough. And the reason is because when we look at the field homogeneity in the neck area, we have a lot of static inhomogeneity as well as dynamic inhomogeneity due to breathing. So these would then create a lot of issues in the diffusion, especially high resolution diffusion MRI. So we need to address these inhomogeneity, both static and dynamic issues. Fortunately, with air coil, which has a continuously conducting loop, we were able to achieve simultaneous MRI and V0 shimming by injecting AC currents, which is MRI RF current, shown on the left here, and the DC current shown in blue on the right here at the same time. And this is extension of our iPress concept to achieve both simultaneous MRI and V0 shimming. Except air coil makes it a lot easier because there's no capacitors along the coil path. We can just simply inject DC currents straight into the coil and take them out. So with that, we were able to get 4 channels into the neck area to acquire image, as well as shim both statically and dynamically. So with this improvement, we can achieve whole brain, whole spinal cord diffusion MRI by placing a dorsal RI, spherical RI here in the spinal cord at bottom of the C-spine, almost to the T section. We were able to track the fibers all the way to the thalamic region, to the somatosensory cortical region, and as well as cerebella. So this is all coming from this very small region in the dorsal column. If you zoom into the brainstem region, you can actually delineate at this high 0.6 millimeter spatial resolution the crossing of the spinal cord fibers into the opposite side or contralateral side of the brain. And this is really a very high spatial resolution that would be impossible before. So we were very glad to see that on the UHP platform. If you take a cross section from the brainstem to the spinal cord, you can actually see the typical butterfly structure, which again is difficult to see with other previous scanner platforms. So we're hoping with this type of advanced technology, we should be able to pick any region in the brain and try to see where we can place minimal amount of electrodes to achieve or reduce the invasiveness of this already low invasiveness surgery. So then we can place the electrodes in a precision fashion to achieve most effective brain stimulation or deep brain stimulation without any adverse effect. So to this end, I'd like to summarize. So the new SIGNA UHP 3T is really an advanced platform that would allow us to develop tools to do a few things. One is to investigate brain microstructure changes related to early neuronal deficit, hopefully before symptoms occur, and improve our understanding of the disease mechanism. And more importantly, I think, is to better plan new treatment options for neurodegenerative diseases. This work would not be possible by my talented Duke colleagues, Chris Patty, Ian Bruce, and Langui Chen in particular on the Muse front, and Ding Darnell, Chuanka Chuan on the RF shimming and simultaneous MRI front, and all the students and collaborators. I'll be remiss not mentioning Paul Dave's team. The Beyond MR team at GE Healthcare has really made this UHP platform, in my opinion, the best machine to study brain microstructure. So with that, I want to thank you for your attention, and I want to introduce our next